This is my logic-based splitter design. To explain the method behind it, I've made this little setup here. If we were to imagine a traffic of trains coming down and we want to split it 4 ways, one strategy we could take is that as soon as a train takes a path, we block it off. And so now subsequent trains need to take the other paths, and then say a train takes that path, we block it off, and then next train takes this path, we block it off, next train takes the last path, we block it off, and then once all paths are blocked off, we open them back up, and so then the remaining trains can take whatever choice they want until they actually do, and then we continue blocking them off as they do. And what this is going to do is it's going to guarantee that each path in a cycle of this blocking off and unblocking, each path is going to be used exactly once, which guarantees that we get a 4-way perfect split. And so the way that this contraption does this is that here we just have 2 paths, and the way that we're going to block off a path is with this little memory cell. We have this combo signal that can see its own signal, so when it turns red, it stays red. And that is reading if a train has taken this path, and so when it has, it stays red. And now this red 2-way signal is going to be red, which is going to force trains to take the other path if you have set ypf.rail underscore first red underscore 2-way underscore EOL to 1. So you would say set that thing 1 and it will set it. And that is required for this part to force trains onto the other track. They will not try ever, unless they're lost or had no orders, they will not ever try to go to the left path anymore. So it is blocked, just like if we were to block a path here. Then as soon as a train goes into this other path, it's going to trip this exit signal, which along with the combo signal that's reading the memory cell's value, is going to trip what this is, which is a NOT gate. It is my preferred way of making a NOT gate. There is a simpler and easier way to do it, which I'll be showing later, but this NOT gate will turn this signal green, which will reset the memory cell, and that is effectively turning all of them green because this path doesn't actually have a memory cell connected to it, and there is a good reason for it. So as we see, this one turned green, and now trains can take the path again. Turns green. Memory cell turns green. And so the reason why there's no memory cell connected to this right path is because if we were to have more than one path, like this 1 to 5 split I have here, imagine what would happen if I converted it to a 1 to 4 split. And so now the one with the backwards PBS, which was providing a penalty to ensure that the trains took it last, well, now that's no longer in the question here, in the picture. It is just the 4 that had memory cells that are going. Now let's watch what the pattern is. We just had 1, 2, 3, and then this one again. Okay. Now wait a minute. Watch what happens when we take this fourth and final one. It stays red after the reset, which means now we're choosing between these 3. And now we choose this one at the end, and it stays red after the reset. Now we're choosing between these 3. So this isn't exactly a 4-way split. And so what is required is a final path right at the end, once all other choices are read, that the trains will take that doesn't have a memory cell attached to it, but will actually trigger the reset. And so that's what this line is here. I have the backwards PBS to provide a penalty so that the trains always take it after this one's already read. And that fixes the problem. So it's basically just memory cell reading whether or not there's a train taking these paths, and then a NOT gate looping around and resetting the memory cell. And the nice thing about this design is, see how I have this 1 to 5 split, which I'm going to revert to its previous version. I have a 1 to 5 split, but it still only uses one NOT gate. In fact, you can do 1 to n and only use one NOT gate. And this is very nice for reducing the amount of logic trains that you need to use, and just wiring in general as well. But it's just the same concept of, we have 4 memory cells for the 4 paths that are going to have a memory cell, plus a exit signal looking at the last one. Those all get combined. Once all of them are read, it trips the NOT gate, and then these 4 signals are reading the output of the NOT gate to flip the memory cells back to green. Another nice advantage about this design is that you can defer later splits as long as you want. So here I have a more organized version of the 5-way split, but as we'll notice, it's not actually a 5-way split. It splits quite a few more times, and it even splits after long gaps, because there's this neat trick we can do to have trains be able to know that there are green paths ahead and to continue driving forward. And that is with a technique called presignal bypass, and that is what this parallel rail is for, with all these combo signals on it. So what the purpose of the 2-way is that this combo signal here will tell this exit signal whether or not there is green anywhere ahead. And what this green signal, this combo signal, is reading is the values of everything down the line and this specific block, because it goes through this 2-way in the other direction to read the value of this path, whether or not it's read. And so the effect of this is that if any paths are green, it'll propagate all the way down and change the entry signals behind it to be green. However, any entry signals after the last green path will be red. And finally, I have this disconnected, so we'll ignore it for now. Finally, we just have the same setup with the final path that triggers the reset. It does not have a memory cell attached to it. As you can see, these had memory cells, this one does not. And we see the problem with this design already is that, well, we really shouldn't have had this train go through the final path already, because as it did, there were green paths before. And we're going to watch that again. Should happen again right here. So there's green paths, but we have this one taking the last path, and that doesn't, since there's no memory cell connected to this, it doesn't actually get blocked, because we've tried to designate it as the last one, but it did not in fact get used last there. And that's a problem. There are ways to mitigate it. This is mostly a result of the long gap we have between the second to last and last paths. So if you minimize that distance, you can basically get rid of most of the problem. You could also get rid of it by having low traffic. And there's another way to mitigate it, which is to reduce the actual length of the path by having more pre-signal bypass trick being used. And so these become more stopping points where the trains will see, if we had, whoops, oh, we had 3 that time, even worse. But once this train went through, these 2 would have possibly stopped at these points because they would see, oh, it's red ahead because the train ahead actually is making it red. And in fact, I think I have this wrong. You would need to have it like that, like a normal pre-signal bypass. I have it changed so that I can use this later, but it would need to be like this, and we should notice that this one stopped, and it stops until it's allowed to go through. However, it still didn't find any other path to go, so it still went down that path. If there was a smaller gap and we had another path there, maybe it would have done the right thing. So I'm going to change this back. Like that, I believe. And it's also important that when you do these intermediate pre-signal bypass like stops, that the signal here is not a 2-way, it's just a 1-way. Because there's actually nothing to read there. If you did make it a 2-way, it would just be outputting green, and then it would always make green for all the previous ones. Not really what you want. So a way we can fix this, and I'm just going to show the whole rest of the design here. The way we can fix this is, well, what if the last path was always red until every other path was red? Then it turned green. That would fix the problem, right? So that's what this NOT gate is for. And so what we're going to do is have the pre-signal bypass read the output of this NOT gate, where the input of this NOT gate is going to be reading all these signals. And what all these signals are is they're reading the values of the memory cells. And so every other path besides the last one is attached to these memory cells, and once they're all red, we're going to get a red signal into the input of this NOT gate, and it's going to output a green signal to this combo, then to this entry signal. And so finally there will be a path at the end that's green, and the trains will actually try and continue on rather than just stopping about here. However, there is one more thing we need to fix, and that is that we do still need to read whether or not a train has taken the final path to trigger the NOT gate. And so we have to route this all the way back to the input of this NOT gate, which is also taking in the values of all of the memory cells, but in addition to the final path. And that will reset all of the memory cells. It may have been easier logistically to have this NOT gate over here and possibly even put this path, since now it's red always until all the other paths are taken. We can actually put it at the beginning. It doesn't even need to be the last one now. However, I think that would probably be less efficient because we would end up with a lot of stopped trains. What has happened here? Ooh. Interesting. Well, I did not run into this in testing, so that's very strange. It appears that this, being the only green path, is blocked. The pre-signal bypass is actually not able to propagate the green signal all the way down over here. So perhaps these or kind of a mistake, at least to put so close to here. Perhaps. I'm not going to claim that this is foolproof. Obviously, we saw it just break right now. But for most intents and purposes, it's not going to look like this. It's not going to have these long gaps. It's just going to be more like this, and probably not a 1:20 split or anything like that. Probably more like this 1:5 at most, maybe a 1:6. And in this case, this is pretty foolproof, or fail-safe rather. But as we can see, it should just work. And so what I'm going to do here is just do a little bit of building. I'll just build one, follow along. So right here I have a simple presignal split, which obviously the trains are too far apart to actually split correctly. We see these two just took the same path consecutively. So it's not splitting 50-50. Well, let's fix that. Let's choose this path to be the one that's like the last path. So we put a penalty there. Oops. And then what I need to do is we have two-way signal, but we don't want the green backward signal to be messing with the logic that is going to be coming up ahead. So we put a one-way presignal right after it. And I want this this block right here to be red. So now that we have that, we make a memory cell. And just from that, as soon as the train takes this path, it's going to turn red and it's going to stay red. And so now they're actually forced always to take this path now. So we need to make the ability to actually reset it. So I am going to have a signal that is going to read the memory cell. And we're going to also have, after a bridge, an exit signal reading whether or not a train has taken the final path. Then we combine those. This and this being red will cause any subsequent signals to be red. And when that happens, what we want is a NOT gate to reset it. And I'm going to use a simpler NOT gate design that is probably a lot easier to build, more foolproof, especially since the design that I usually use, you sometimes have to mess with the pathfinder to get the train to actually do what you want. But this will be our input, this will be our output. And the way that this NOT gate works, actually I'm going to do it this way, is you make this shape, the loop with the kind of a half loop going through it. And you put the signals like that. So you want to make sure that the exit signal is looking towards the input, sorry, the entry signal is looking towards the input, and then the output, which is this combo signal, is going to read whether or not there's a train here, and also through this exit signal whether or not there's a train here. Actually, that's supposed to be one way, yes. And then let's get our logic trains in. And what we're going to do is, I found this to be the best way to do it, is to have two logic trains of length 1, and just no orders, you set them off. Looks like this one needs to ignore that signal. Oh, I have this one backwards. That's why it looked weird. Okay, and so this signal stays red as long as they're spinning around, but as soon as, yeah, we just had this one taken, then it turns red, and for a split second, what was going to happen was these two trains will stop at this entry signal. One will stop here, one will stop here, which means these two blocks are empty, and that lets this signal be green. And that's how that NOT gate works. The reason I don't use it is because it uses two trains instead of one, and they're also longer. I think that might cause more performance issues, which I have run into in my games, so I prefer the other design, even though it's more complicated and harder to set up. But there we go. That is how you make my splitter design. I just want to get another shot of, okay, it's red. I can't even catch the moment, it's so fast. So just know that this NOT gate works. So here we will be able to find some of my splitters in action in an actual game. I have a sideline hub here where the main line is 4 lanes each way, and the sideline is just 1 lane. So here is a good example of a 1-to-4 split. Here's the right turn from the sideline, splits 1, 2, 3, and finally 4 ways onto the main line. And as we see here, we have very similar circuitry. We got 3 memory cells and 1 NOT gate to reset them. This part is not connected here, don't worry about it. It is just this part. I have also used as a penalty some level crossings. And the nice thing about using level crossings is that they don't break the signal block. And so I did that. This is actually kind of an old design. I did that when I didn't know how to do the pre-signal bypass correctly, and so this kind of proto version of it required that there weren't any signals between, so I could not put a backwards PBS there that would break the signal block and it would break the system. So this is the solution I came up with. And back when I was explaining everything else, why are you empty? Well, it's not empty, but it's a self-regulating network. You're supposed to be full. Back when I was explaining things, I did notice that problem with the third design, and it stopped me in a thought. I never finished the thought. But what it was is that the pre-signal bypass basically will stop trains before they make a bad decision, or any decision at all. They will stop in front of a split and just wait there until anything turns green, and then they will go towards the green. And what that does is it helps them to not all pile into the last possible path, and skip all the other paths which would have turned green if they just waited. And so that's basically the idea behind that. The other thing that I wanted to explain a little better is I never explained why the last path needs to not have a memory cell, and that's just simply so that it stays green after the reset. If it had a memory cell, it would stay red, and we would have that same problem we were observing in the second design when I broke it, which was that a path, let's say a path on this 1-to-4 split, a path which would be the final path, would get taken, but it would stay red for the whole next cycle. And so instead we were actually splitting 3 ways among the other 3, and then one of those would stay red for the next cycle, and then we split 3 ways among the other 3. And so it doesn't actually make a true 1-to-4 split. And the final thing to say is that if you do end up deferring your splits really long distances, just know that you can avoid most of the issues by just making sure that the last 2 splits, or the last 2 paths at least, are very close to each other. or even the last 3 or 4 if you have a really large gap before them. And that basically gets rid of most of the issues that we ran into with the third design. But that's basically my splitter design right there, in use. Thank you for watching.